Hello and welcome to this virtual 2023 awards ceremony. We are here today to celebrate and crown TecQuipment's 2023 Student Competition winners. So let's go find out who the winners are. Thank you to all the teams and institutions that entered the TecQuipment competition. There was a wide variety of entries using a variety of equipment. The standard of entries on the whole was high, and the judges were unanimous in their selection of an overall winner. We thank you for taking the time to create these videos and hope that by doing experiments slightly differently than normal, this developed your thinking and knowledge and made it fun. First, we would like to offer our feedback on the videos before we reveal the results. From all the videos submitted, the videos that scored higher had some of these elements. They introduced the equipment and experiment clearly, provided background as to why the experiment was being performed, its purpose, was it proving, or contradicting a theory. They critically analysed the results that were presented, going into real depth about what the results meant and if this was expected, and if not, was there a reason. They showed and talked through the experiment. Feedback for improvement. Marks were lost for not clearly introducing or explaining the experiment. We needed more visual emphasis on what the experiment was, so whether a photo or a video, as this makes a better presentation. Show and clearly explain your results. Show graphs and calculations, then explain what this shows. We also want to have a shout out to the teams who provided a post-lab overview of how to clean out the equipment after the experiment ended. This was a nice extra. Included real-world examples. Provided diagrams of what the experiment looks like inside to help explain the experiment procedure. Provided relevant theory and linked this to results. By doing this is how you get high marks. On a fun note, we also wanted to commend the team that had renamed the equipment used after introducing it formally. Now, onto the results and what everyone has been waiting for. So, from each institution's videos were judged in round 1. And the one winner from each institution was then put forward into the final. So from the 3 universities, the winners of each are
Hello everyone, my name is Sheikh Benisi. And I'm Jim Sanosavo, and we're both mechanical engineers here at SUNY New Paltz. We're just some of the individuals who get to work with the TecQuipment wind tunnel demonstrator.
Although, here at SUNY New Paltz, we like to call her Betty for short.
Betty is a small-scale wind tunnel featuring a 3-bladed wind turbine, and it's capable of drawing more than 15.5 meters per second of air. She has an adjustable lever that controls the yaw of the blades, as well as a variable pitch dial that is accessible on the front panel interface. This panel also features controls for the fan speed in Hertz, as well as turbine speed in RPM. Additionally, Betty can also send data to our provided computer software, VDAS. The VDAS software can record all input parameters like yaw angle, pitch angle, RPM, and fan speeds. However, the primary output measurements are power and torque.
See that red thing in there in the corner? That's the anemometer. It can be used to measure the wind speeds across the diameter of its opening. You know, to get the incoming airspeed, also known as its velocity profile.
Our research specifically focuses on the compatibility of making 3D printed turbine blades for use within the demonstrator itself. Basically what we did was we replicated the blades that were provided for us by the company and 3D printed our own.
This here is the HVAMC, also known as the Hudson Valley Additive Manufacturing Center. Using this campus resource, we were able to fabricate our current and any of our future blade designs. This thing right here is the PolyJet. Using this machine, we're capable of printing objects comprised of different materials at varying ratios.
In order to ensure that the blades we fabricate meet the safety requirements laid out by TecQuipment, we perform material testing in the form of tensile, flexural, and impact tests on several materials available through the HVAMC. The results of the tests show that the blend Vero Agilis 25 is the strongest of the chosen materials. These meet the requirements laid out by TecQuipment for use within the demonstrator, so we decided to use this material for all custom blade models from here on out. In the graphs shown here, the performance of the provided blade set with cross-section NACA 6409 is displayed alongside the performance of our printed blades in the same geometry. Therefore, we can conclude that the difference between the two is negligible.
Here is one example of a performance curve generated for our printed turbine. This graph shows the power output under a constant wind speed of 9.4 meters per second. Each curve represents one pitch angle. The y-axis shows the power output and the x-axis shows the turbine speed. This testing can be performed at multiple wind speeds to understand the turbine's performance under any combination of input conditions.
Drawing from our experience with 3D modeling softwares like Rhino 3D and SolidWorks, we intend on creating wind turbine blades comprised of multiple different NACA airfoil cross-sections.
Thank you so much for attending our research presentation.
Thank you. We wanted to thank our contributors to this research.
This is our TecQuipment Student Competition enrollment. Our team is Braden Dillinger, Carson McLaughlin, and Colin Clark. We all are mechanical engineers at the University of Michigan Flint. We'll be analyzing two different heat exchangers. Heat exchangers are used to cool down coolant that has been heated from the engine. So the coolant will travel through tubes and it'll get cooled down by the air and sent back through the engine to cool it down and prevent it from overheating. Our proposed research question is, how does the overall efficiency improve when varying airflow rate of an automotive compact heat exchanger versus 16 tube finned experimental heat exchanger?
So here's the machine used to test these heat exchangers. It is called the TQ-TD1007 water to air heat exchanger. And to set up this machine, we first place the heat exchanger right here in the middle between these two steel frames, and then we clamp it down using these clamps here. Then we'll connect the pipes. The bottom one here is the water supply, and the top one's the water return. After that, we'll plug in our communication, which will relay the information to our computer, which will be collecting our data. After that, the machine is ready to be powered up, and here is where we'll set our temperature, and then we'll turn on our fan and our water. And here's a valve here that will adjust the liters per minute that we want the water rate, and then here's a sliding gate, which will adjust the outlet pressure. So here are the schematics for how the air travels through the machine. And so as you can see, this is the inlet, and then it'll blow over the fan. The fan will push it over through the heat exchanger and out the outlet. And then over here is where we'll be measuring the points on the machine where we'll be measuring the temperatures. So the TAs are all the air temperatures, and the TWs are where we'll be measuring the water temperature. Here's our heat exchangers we used for this competition. The air will be moving across the inside of these frames and be cooled from the tubes that are supplied with water. We add fins in the heat exchangers to help to extend the surface area and help with overall efficiency. And as you can see from this picture, you can see how much more compact the car heat exchanger is. The experimental setup, we have two types of heat exchangers, which we just explained. Then the connection is you can either set it into parallel or series, and we use parallel. The heater tank temperature is 60 degrees Celsius, ambient air pressure is 100, orifice diameter is 100 millimeters, water flow is 0.75 liters per minute, and our airflow rate, which is our variable for this experiment, we go from 200 to 150 to 100 to 50 to 25. And here's a demonstration of our experiment.
So these are the results that we received from the two experiments, with the compact heat exchanger being on the top and the fin being on the bottom. In this graph, we can compare how much water power is being exchanged to the air mass flow rate. We can clearly see that the compact heat exchanger exchanges about 2/3 more than the finned heat exchanger, with both heat exchangers decreasing as the air mass flow rate increases. In this graph, we are now comparing the mean temperature efficiency to air mass flow rate. We can see that the compact heat exchanger with the increased surface area is much more efficient at transferring heat than the finned heat exchanger that has less surface area, with both heat exchangers' temperature efficiency staying fairly constant as the air mass flow rate increases. Now finally in this graph, we are comparing the heat transfer coefficients of the two heat exchangers to the air mass flow rate. We can see that the compact heat exchanger is able to exchange much more energy than the finned heat exchanger at all airflow rates, with both heat exchangers getting slightly better at exchanging heat as the air mass flow rate increases. As we can see, the compact heat exchanger outperformed the finned heat exchanger by every metric. This outcome was expected because the compact heat exchanger is a real heat exchanger, and we are comparing it to a heat exchanger that was meant more for a lab setting. But we did not know that the compact heat exchanger would perform better than the finned heat exchanger by such a large margin. Overall, from this competition, we can now see the connections between how an experimental heat exchanger will compare to a real-life application of a heat exchanger.
That is the end of our presentation. Thank you for watching our student competition.
So, round one's winners are from Sunny Newport's team 1, James and Jake. From York College of Pennsylvania, team 3, Zach, Jabin, Avery, and Kofi. From the University of Michigan Flint, team 3, Brandon, Colin, and Carson. So, from these 3 teams, who will be our grand final winner? Drumroll, please. And the winner of TecQuipment's 2023 student competition is the University of Michigan Flint Team 3, Analyzing Heat Exchangers. So congratulations to Braden, Carson, and Colin. The winners presented a well thought out and interesting comparison of heat exchangers with in-depth coverage of experiment background, overview, and demonstrated the equipment and provided results that they then drew appropriate conclusions and critically analysed their work. Well, that's it. We have found our winners. For those of you who are not in your final year, we hope to see you competing again next time. We enjoyed judging the entries and thank you all for your participation. Thank you and congratulations to our winners. Your prize money and trophy will be heading to your university shortly. Have a wonderful day, and again, congratulations to all and especially our winners.